Calculus involving exponential functions and logarithms. The logarithm log is the inverse process to raising to a power. So as a power we have 2 cubed equals 8. We call that exponential form. As a log we write log of 8 to base 2 equals 3. That's logarithmic form. Note I use the word base. We cannot say log of 2 to the 8. So we say log of 8 to base 2 equals 3 or log base 2 of 8 equals 3. A bit of an explanation. Notice that the 2 is the base of the power. It's also the base of the log. Base is below the line, the suffix. The number. And the exponent. There's the exponent. And that there is the exponent becomes what the log is equal to, meaning that a log is an exponent. And that's very important. And we're going to use that fact on a number of occasions. A log is an exponent. It's the exponent which 2 needs to get 8. So, writing in exponential form. That means base to the exponent equals 25. Base in the log remains base in the power. The log, that's what the log is equal to, so this is the log, is equal to the exponent. Base to the exponent equals the number. Now that has no base, or does it? We work in a decimal system, base 10, where we have units, tens, hundreds, thousands, so that's called the decimal system. Now in this case, when we have log of 100 without a base, it's automatically understood that is base 10. So therefore we could have written that as log of 100 to base 10, but it's unnecessary. Would mean base to the exponent equals the number. Once you've done them, pause. Once you've done them, continue. So 7, the base to the exponent is the number. And that can be taken further. No base? Yes, base 10. Bit of investigation here. Log of 7 to base 7 equals x. Means 7 to the x equals 7, which is 7 to the 1. And of course 7 to the x equals 7 to the 1 means that x equals 1. So what does this mean about log of 7 to base 7? Well, we started with log of 7 to base 7 equal to x. Now we know x is 1, therefore log 7 to base 7 equals 1. Log of m to base m, we'll treat that in the same way. Of course, that's based on a premise that m is greater than 0. We'll come on to that as well. You cannot have log of 0 or base 0 or log of a negative or base negative. and 1 is 5 to the 0. So therefore log of 1 to base 5 is 0. Now we're generalizing it more. Notice once again that k must be greater than 0. So log of 1 to any base is equal to 0. Now this looks as if it's a repetition of the previous one, but it's not really, because e is a very different number with particular properties which we're going to be dealing with a lot. But at the moment we could treat it the same as any other variable. We can't do that. You cannot raise 2 to a power to get a negative. Therefore, log of a negative is impossible. And if the base is negative, that's also impossible. Three rules to remember. Log of a number to the same base as 1. There we are. Notice a greater than 0, of course. Log of 1 to any base greater than 0 is 0. Log of 1 equals 0. And log of negative numbers or 0 does not exist. If you have something in logarithmic form and you have a problem working it out, you could always write it in exponential form. There we are. And now we can solve for x. And that means that log of 81 to base 3 is 4. But of course calculators nowadays have a log of a to base b button, so it makes life much easier. Now we are to what are called natural logarithms. Same as all other logarithms, except now the base is e. In our decimal system, when we write a log without a base, that means base 10. Well, now we have base e, and we have a way of writing that too without having to write the base. Number of valuable properties. Couple of points of interest. There's the actual derivation of e, where e comes from. Sigma n equals 0 to infinity, 1 over n factorial, where n factorial is n times 1 less times 1 more less times 1 more less, etc. So in other words, 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. So, when n is 0, 0 factorial is in fact 1. 1 factorial, 2 factorial, 3 factorial, 4 factorial, continuing to infinity. E is therefore an irrational number. The gradient of the function f of x equals e to the x at x equals k is e to the k. It is its own gradient, it is its own derivative, in other words. Therefore, the derivative of e to the x is e to the x. Now, the natural logarithm uses e as a base, so log of x to base e is the natural logarithm. And we write it as ln x, like that, and we don't have to write the base, and we pronounce it ln x. Now, when we differentiate e to the x, we get e to the x straight back. We've mentioned that. When we differentiate ln x, we get 1 over x. So, derivative of e to the minus x, well, notice that that there is a composite function. Outside function, e to the u. Inside function, negative x. When we differentiate the outside, we come straight back with e to the u. Differentiate the inside, we get negative 1. And the chain rule says derivative of outside times derivative of inside. E to the u times negative 1. Which simplifies a bit. Another one, same thing. Composite, chain rule, outside e to the u, inside sine x. Derivative of sine is cos. Now this we could differentiate as a quotient rule as it is there, but remember that if we have a binomial over a monomial, it's probably easier to write it each one separately over ln x, as I've done there. Because this is going to cancel and give us 1, and when we differentiate 1 we get 0. So we'll end up with just that. And that is a quotient rule. Derivative of top times bottom minus top times derivative of bottom all over bottom squared. Derivative of 1 is 0, so it's gone. Derivative of x, 1 times ln x minus x times derivative of ln x, which is 1 over x. All over ln x all squared. And x times 1 over x, negative 1. Here are some exercises to try. Pause, do them, then go through the answers. Remember that 4 root x means 4x to the half. And we have a composite rule, so therefore e to the u and times derivative of that, which of course is that. That is product rule. There it is there. And that differentiated comes straight back with minus e to the x. Now we have e to the x cancelling out, so we x times e to the x. A product rule again. Derivative times e to the x plus that times derivative. When you multiply out and simplify, a whole lot of terms cancel one another out, and there's our final answer. Another product rule, derivative, the sine terms cancel one another out. We've got 2 e to the x cos x terms. Ln. Well, outside function ln, so that therefore differentiates to 1 over. Inside function 4x, so we must multiply by 4. This is 1 over x. The outside function here is something cubed, and the inside function is ln. So therefore 3 times ln x all squared times, and there's the derivative of ln x. Here's a product rule. It's derivative times that plus that times derivative. Derivative of ln x, 1 over x times that as it is, plus ln x as it is, times derivative. Derivative e to the x, derivative of the x, 1. Composite rule. Notice that this one is a product rule and a composite rule within it as well. That simplifies to that. composite rule with a quotient rule. Derivative of ln of x, well, ln u is 1 over u, so therefore 1 over that, so we've inverted it. Then that is differentiated. The inside function is differentiated using quotient rule. Goes down quite a bit. Product rule with a composite rule inside the bracket. Derivative, and notice there's a sin x, cos x there because this is a composite rule, times that, plus that as it is, and we differentiate that. Notice that the 1 goes, derivative of 1 is 0, ln x squared, so you get 1 over x squared times, and that's the derivative of the x squared.